Hey, all you brilliant science scholars, it's Mr. Harrison here from school, and I'm here to show you, or rather take you on a guided tour of this periodic table. The full name would be the periodic table of the elements, because each one of these boxes right here is a different element. So let's start with that, the element box. Here is helium. This here, the He, is called the chemical symbol. Symbol for helium is He, capital letter first, then a lowercase, because every element starts with a capital letter. Then somewhere on the box, they change up where on the box, but somewhere you're going to have a whole number, which in this case is 2. And then you're going to have the name for the element, which is helium, and then a number with a decimal, in this case 4.003. The whole number is called the atomic number. So the atomic number for helium is 2. The decimal number is called the atomic mass, or the mass number, or sometimes the atomic mass number, but some mass is in there somewhere. The atomic number, the whole number, in this case for helium 2, tells you that the number of protons in that atom, or in an atom of that element. So every helium atom has got 2 protons. And here's how I remember that. You can't possibly have a fraction of a proton. You can't have 1.7 protons. You can only have 1 or 2 or 3 or 4 or 5, only whole numbers. That's why the whole number is the atomic number, because you can only have whole entire protons in an atom. The mass number down here, 4.003, can be a decimal because it's an average. The mass number tells us, on average, the total number of particles that are in the nucleus of that type of atom. So that means in a helium atom, there are 4 total particles in the nucleus on average. On rare occasion, there could be a little more than 4, which means there could be 5, but most of the time, there's 4. And if there's 4 particles in the nucleus, we know that the only particles that can be in the nucleus are the protons and the neutrons. 2 of those 4 total particles are protons. That leaves 2 to be neutrons. So it tells me that the average helium atom has got 2 protons and then 2 more neutrons to give us 4 total in the nucleus. You might be thinking, okay, that's great, Mr. Harrison, but what about electrons? Well, here's the electrons. It's very easy. We assume that any of these elements are neutral, which means they don't have a +1 charge or a -1 charge or anything like that. If they're neutral, they have to have the same number of positive protons and negative electrons. So a neutral helium atom has got to have 2 protons and 2 electrons. So if it's neutral, the atomic number tells us not just the number of protons, but the number of neutrons. So just to review, chemical symbol, He, atomic number, 2, the whole number, atomic mass, 4.003, and then the chemical name. So that's helium. Now, each one of these boxes is going to look like that, just with different numbers there. So lithium's going to have, a different number. Beryllium's going to have a different number, and so on. So that's each box. Now, before we get into the groups and periods, I want to draw your attention to these red elements right here. These red elements kind of form like a stair step, a staircase. In science, we call this the stair step line or the zigzag line. And the zigzag line isn't actually drawn on here, so I'm going to draw it with my cursor, so follow along. The actual official stair step zigzag line would start under boron right here. It goes here, then down, then here, then down, then here, then down, and here, then down. And as you can see, most of the time, there's a red box on either side of that staircase. The only exceptions would be aluminum and polonium. And polonium, and most of them would be also red along with the astatine. So here's your stair step. Each box on each side is red, except for aluminum. And that stair step line is like the dividing line of the table. Anything touching that stair step line on either side, except for aluminum and sometimes polonium, Anything touching that stair-step line, so boron, silicon, germanium, arsenic, antimony, tellurium, possibly polonium, and definitely astatine, that's called a metalloid because it's like right in the middle. It's not either or category. It's not a metal and it's not a non-metal. It's a metalloid. Like we talked about adding the word ish to the end, like it's metal-ish. That's kind of another way to say it. It's a metalloid. It's kind of a metal, but it's kind of not a metal. Okay? So remember, here's our stair-step line. And anything to the left of that stair-step line, so everything over on this side is a metal. Click the metals button. Here's all. Metals are anything to the left. Technically, some of these not metalloids are considered technical metals, although they're not in the truest sense fully metals. Anything to the right of this stair-step line is a non-metal. Now you notice when I clicked on non-metals, there's one of them that looks like it's a metal that stays there, and that's hydrogen. Hydrogen is the only rule breaker with this. It's the only metal, the only non-metal that's in the metal section to the left. The non-metals include hydrogen. That's the one rule breaker. That's why it's also purple. So just to review, metals on the left, non-metals on the right, metalloids in the middle, which reminds me of a song. We're going to consult our friend Beyonce. There's a little song, bear with me, that will help you remember where the metals and the non-metals and the metalloids are. It goes a little something like this. To the left, all the metals are in a box to the left. Non-metals on the right, non-metals on the right. Then you got the metalloids in the middle. Then you got the metalloids in the middle of the table. Let's try that again. To the left, all the metals are in a box to the left. Non-metals on the right, non-metals on the right. Then you got the metalloids in the middle. Then you got the metalloids in the middle of the table. So I'd like to say that I'm sorry for getting that song stuck in your head, but in truth I'm not, because it'll help you remember that the metals are in a box to the left, non-metals on the right, and the metalloids in the middle. Those are the three sections. Metals, they include the metalloids there. The metalloids are here, and the non-metals over here, plus hydrogen. And you might be wondering, well, what's the case with these guys? Why don't they disappear ever? Well, it's because they are borderline metals. They're actually a very unique category of atom. And there's another something that's pretty unique about these. See how these each have, as we read it like a book, left to right, top to bottom, these atomic numbers get one bigger each time. And you'll notice it skips from 56 to 72 right here. And then it skips from 88 to 104 right here. That's where these go. 56, 57, 58, 59, all the way to 71, and then back up to 72. So the true table would have these two columns fit right in here. Now when we get to the actinides, these bottom row, we got radium, and then we have actinium, thorium, it's hard to read it, protactinium, and uranium. You probably remember uranium because that is a version of that is what we use for fission, nuclear energy. Uranium is the largest naturally occurring atom on Earth. That means neptunium and plutonium and americanium, like these are all man-made. We can only make them in a lab. And if you notice, 103 lawrencium, and we got rutherfordium up here. All of these are also man-made, all the way up to tennesseum and organessium. Some of I'm honestly not even sure how to say this one because we don't really need to know about it for this, but it's a relatively new discovery. All of these ones are man-made, and everything past uranium, so starting with 93 neptunium, is all man-made. So now that you've got the basics of the sections, the metals, the non-metals, and the metalloids, we need to talk about groups and periods. We'll start with the periods. There's two ways to classify the table, either vertically, up and down, or horizontally, left to right. Periods deal with horizontally left to right. The first period only has hydrogen and helium and nothing else. The second period has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So there's nothing in this area here, but it's got 1, 2, 3, 4, 5, 6, 7, 8 atoms. Or elements, I should say. Group 3, we go down 1. So all of these periods would have like a 1 to the left here, and then a 2 here, and a 3, then a 4, then a 5, then a 6, and so on. In the period, tells us when we have to reset the outer valence electron shell. Now, a quick review, because I know we've talked about this in the slideshow and other areas. Every one of these has got electrons, if it's neutral. But there's electrons and then there's valence electrons. Valence electrons are just the outside shell electrons. The electrons in the outermost shell are called valence electrons. And these valence electrons are really, really important because they tell us how these are going to tend to make bonds in one-to-one ratios with other elements. And not only can we describe what we see, but we can also predict what will happen. These are literally like predict the future type skills that you can have by reading this table. So if you start with hydrogen, hydrogen is in period 1. There's only one other element that's in period 1, and that's helium. There's only only 2 elements in first period? Why is that? Well, that's because the first electron shell, the first orbital, remember from Schrodinger, the first electron shell only holds 2 electrons. And because it only holds 2 electrons, if you want to add a third, you can't put it over here. You need to drop down a period to lithium. This is 1 electron, 2 electrons. The third electron is down in the second period, which means it has another shell. And although it has 3 total electrons, 2 of them fit in the first shell. So the outer shell, the valence shell, only has 1 electron. Then if you add 1 more electron to that, you get beryllium. That's 4. If you add another electron to that, you get boron. And by the way, when I say I'm adding electrons, I'm also adding 1 proton because it has to be neutral. If you add 1 electron to boron and 1 proton to boron, it becomes carbon. And keeping it neutral, adding a proton and an electron to carbon makes it nitrogen. Adding a proton and an electron to nitrogen makes it oxygen. Adding a proton and an electron to oxygen makes it fluorine. And adding a proton and an electron to fluorine makes it neon. And then if we want to add another one to make it 11 total protons and electrons, we can't add it here. The reason is neon already has a full valence shell. So we've got 1, 2, 3, 4, 5, 6, 7, 8 elements in period 2. And that tells me that the second, period 2, second electron shell only holds 8 electrons. Once we had to add another one, we bump it down to sodium, which is number 11. But sodium, even though it has 11 electrons total, 10 of them are filled up, 2 here and 8 here. So it only has 1 in the outside shell. So you might be noticing the pattern. 1 valence electron here, 1 valence electron here, 1 total electron, but 1 valence electron here. So each of these in group 1 has the same numbers of valence electrons. So here's group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. This is what they have in common. They're extremely reactive because they have 1 valence electron. They don't like to have a full shell plus 1. They want to drop that electron and go down to the shell below it. So sodium really wants to get rid of 1 of its electrons and go down to that shell below it. Because then it has a full shell, because if you remember, sodium, if you drop 1 electron, you're down to this configuration. Potassium, if you drop 1 electron, you're down to argon configuration. And that brings me to my next point, which is this group here: helium, neon, argon, krypton, xenon, radon. We don't count this one because it's man-made, but I mean, it counts, but we're not going to talk about it. This is called group 18. The other name for this is called the noble gases. Noble gases are famous because they are the happiest group. They are fully stable. They literally will react with nothing in nature. They never react with other atoms. They just exist as single atoms. And there's a reason for that. Helium, and neon, and argon, and krypton, and xenon, and radon, they all have full outside valence electron shells. So they're not really desperate to take one extra one, and they also don't want to give anything up because they have exactly what they want. They're totally full. That's why if we want to add another one, we got to skip down to the next period. So vertical groups, horizontal periods. Periods tell us how many shells you have. Groups are aligned with the same number of valence electrons. Not total electrons, but outer shell electrons. So we're going to start with noble gases. Noble gases are like the goal of every atom. They want to get to a full shell. Remember that group 1 has one extra, right? It's got a full shell plus one extra. So group 1 really wants to just give away that extra electron. And remember, as you read it like a book, left to right, top to bottom, each time you move to the right, you add one electron. So let's look at fluorine. Fluorine's really close to neon. That means it's one electron away from having a full valence shell. So it's very unhappy like that. It really, 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 really wants to take another electron from another atom because then it would have a full shell. Chlorine, same way. It's one short of argon. One short of the argon electron configuration. So it really wants to take in one more valence electron so that it has that argon full shell. And bromine is one short of krypton, so that wants to get one more, and so on. And there's a rule that tells us that at least applies to the first 3 periods, and then all the way up to calcium number 20. And then we sort of stretch it later, but for you, that's all you're going to have to know. Later on in high school, maybe a little more. And the rule is called the octet rule. You probably recognize oct as a prefix from the word octagon and octopus. Octagon has 8 sides. The octopus has 8 legs. Oct means 8. So the octet rule says that the full shell for neon and argon and krypton is 8 valence electrons. Now, helium's the rule breaker because it only has 2 electrons total. But remember that first shell only holds 2 electrons, so it's full with 2 electrons. But neon and argon, they want to get to 8 valence electrons. The rule is group 1 has 1 electron. Group 18 has 8 electrons in the outer shell, not total, in the valence shell. Group 2, which is beryllium, magnesium, calcium, strontium, barium, radium, has 2 valence electrons. So it's 2 extra from that full shell. Group 17, which is fluorine, chlorine, bromine, iodine, astatine, they all are 1 short of a full shell, so we consider them to have 7. 17 has 7. 18 has 8. 17 has 7. By that same rule, 16, which is oxygen, sulfur, selenium, tellurium, polonium, those all have 6 valence electrons, or 2 short of a full shell. So they want to pick up 2 extras. Fluorine and chlorine want to pick up 1 extra. And of course, the name for this is the noble gases. The name for the first group is called the alkali metals. The name for group 17 is called the halogens. And the name for group 16 you don't need to know, but it's called the oxygen group because the oxygen's the first one. What you do need to know is group 1 has 1 valence outer electron. Group 2 has 2 valence electrons. Group 16 has 6 valence electrons. 17 has 7 valence electrons. And 18 is full with 8, except for helium only has 2, but it's still full. So, as you can imagine, if you've got lithium or sodium or potassium running around with that extra 1 valence electron, and they're not happy about it. We all have that friend that like can't handle being single. If they break up with their significant other, they're back in a dating couple within like 20 minutes. That's what these guys are like. Group 1 and group 17 hate being single. The reason is because they're almost full. They're so close. So fluorine's going around like, help, help. I need 1 more electron. Help, somebody help. And then anything in group 1, lithium, sodium, potassium, they're like, hey, I got this extra electron. Anybody want it? And so then they lock eyes and finally meet, and they're like, oh, wait, I have one extra? Fluorine's like, oh, I need one? We should pair up. We should be buddies. So then lithium donates or gives away that extra electron to fluorine, and fluorine just takes it because group 17 is the greediest of all the groups. They want to take every time, just one of them. And then they're buddies because lithium drops down and has a full shell with the 2 electrons, or sodium drops down and has a full shell with the 10 electrons like neon. And then fluorine has a full shell because it adds the electron that it took from the group 1 element, and it's like just like the neon with the full shell. And then chlorine adds one, and it's just like argon. Okay, so either way, they're happy because they have a full shell. Now, group 16 is a little different, but still similar, also reactive, but they're too short of a full shell. So they're going around like, help, I need 2 more electrons. I'm almost full. And then group 2's over here like, hey, I got 2 extra electrons. Anybody want them? And so group 2 and group 16 will bond in 1-to-1 ratios to solve both of their problems, just like group 1 and group 17 will. So group 16 will take 2 of the extra electrons that beryllium or magnesium or calcium has, and it'll bump them up to the noble gas configuration of a full shell. All right, I know that's a lot of information, but hopefully that's helpful to you. So go ahead and move through this, watch it again if you want to, and answer the questions that are attached to this post.